Okay, sound, check. That there, we'll put that, start class. Good morning, everybody. Stand by as we get the last few things going here. Bum, bum, bum. Okay, welcome. As I remove the trip hazards here from the office studio here in Berkeley, California. Many of you may be planning your trips back to Berkeley, California. Hope we see you. We have two today, tomorrow, and Thursday left in this class, and then we have the final Friday evening. An announcement went out on that to you guys yesterday. So that covers a lot of the details. Many of the details you know already. Comprehensive exam, 3 hours, 60-ish, between 60 and 70 questions probably. Format you will recognize exactly. Some of the problems you will recognize exactly because they will come directly from homework and previous exams. So that's where you should focus your review. We will finish up our acid-base discussion today and talk a little bit about electrochemistry, and then we'll ease on into the final. So I wanted to review yesterday. We talked about a ChemQuiz that I went back and edited, so it makes sense now. So we had a ammonia in water, and that will form ammonia and the conjugate acid. So that's a weak base, weak acid interaction. And we know when those two concentrations are about equal, that there'll be a buffer that will resist the change in pH. And weak acids buffer around their pKa value in pH. So if your pKa value is 4.5, then you'll have a buffer, you'll form a buffer around pH 4.5. And you literally make these things. If you want the buffer, you put the acid or the base, whichever one you want, in solution, measure the pH, and then you titrate, you add acid or base till you get to that pH. So you don't try to do a lot of measuring to get the equal concentration of this and this. You put one of them in and you titrate it. If you put the acid in, you titrate it with the base to get to the where these two species are equal. Or if you put the base form in, you add a little acid and get to the point where these two concentrations are about equal. And where they are equal, the pH will be the pKa of the weak acid. So that is the situation we have here. We started with ammonia, the weak base in solution. It comes to equilibrium with this weak acid. The pKb for that is around 5. So that's a weak base. When the pKb is around 5, depending on what the concentration we put in there, the pH might be around 8-ish, 8 or 9. We could calculate it. We want it to buffer. So these two compounds form the buffer when their concentrations are equal. And the pKb, I think I was calling this the pKa yesterday, which is maybe, I forget, I should go look at the tape. But the pKb of this base determines that equilibrium. I need to get equal concentrations of these two. And when I have equal concentrations of those two, you notice I've written this as the NH3, H3O plus going to NH4 plus and H2O. That's the reverse of the weak acid reaction. It's not even the weak base reaction. I've written it like that because I'm anticipating we're going to add acid to change that into this. But that reaction, we also know a K for. That reaction is mediated by the Ka of that. And so we can calculate the Ka of the weak acid because it's related to the pKb. We're turning this into that by adding an acid. So that actually answers the question. There's if we want to get equal concentrations of this, if you just put the weak base in solution, you won't get equal concentrations. You'll get to weak base. You'll get mostly the base. So to get equal concentrations, you have to add acid. So that's the buffer you can make, and you have to add acid. Where the pH is, you have to determine when those concentrations are equal, the pH will be the pKa of the weak acid. You can get the pKa of the weak acid from the pKb of the base plus the pKa of the acid have to equal 14. So the pKa of the weak acid is around 9, and that's where that will have its first buffer region. So that buffers around pH 9. To get it, we add ammonia and then acid to get those two things in equal concentrations. And the pH will be a 9, and of course we have to add acid to make that happen. And we talked about doing this for polyprotic amino acids. So here are our amino acids. Again, to review, they have acid and base components, acid and base subgroups, side chains, we call them. There's the amino acid part, and then there's a side chain. So they all have an amino acid part, and then they have various side chains with various chemical functionality. They form polymers in your body that makes proteins, and those proteins fold up based upon many things, but based upon, in part, the interactions, the hydrogen bonding and the plus-minus charge interactions on the various parts of the polymer. And the various parts of the polymer are the amino acid side chains. So the backbone of the polymer is the amino acids connecting together, amino acid, amino acid, amino acid, and then their side chains stick out off the polymer and help determine the structure and the functionality of the protein. We talked about something important that is sometimes confusing to people. I talked about when I used this terminology. When does that proton come off? So review that slightly. I've written this as the base form here. So that has a hydrogen attached in the acid form. And when that hydrogen leaves and you have H plus and the base form, the pKa of that acid is 2.2. That means whenever the pH is 2.2, there's equal concentrations of the acid in the base form. So the acid form, here's the base form. The acid form still has the proton attached. So there's equal concentrations at pH 2 of those two forms. If you go beyond pH 2, up in pH, more basic, then these protons continue to come off. And we know they're, the ratio is like 1 in 10 by the time you're 1 pH unit above. And it goes rapidly towards only the base form. So this proton comes off around pH 2. It's about halfway on in pH 2. You go beyond that, and it comes all the way off. That is, the basic form is the predominant form in solution. And you can force it to do that by adding base. That's what a titration is. Force the acid forms to the base forms. So that proton is absent above pH 2. So we've written the structures at pH 7. So we're 5 units above the pKa here. So we're way to the basic side of pKa. That is nearly 100% the base form. But this pKa is 9. We're on the acid side at pH 7. We're on the acid side of that. We haven't even started to get to pH 9, where it would be half and half. So this is all the acid form, because we're on the acidic side of its pKa. And so on. You can make those connections comparing the pH to the pKa of the acid. So that's lysine and tyrosine. And then we looked at a actual protein. This is horseradish peroxidase. And this very important protein, we have many peroxidases in our body. They have tremendous biological functions and keeping us healthy in our immune system and other things, of course, just generally healthy. The structures, we said, these alpha helices and beta sheets, when it's folding into a sheet, it's called a beta sheet. Here's an alpha helix in purple, and it beta sheets over here, and then there's another alpha helix here in orange. So it's just a kind of cartoon of the whole chain, and the side chains of the amino acids are, sticking off the sides of this main chain, and they interact with each other based on their charge state and the potential for hydrogen bonding along those chains. So that keeps our protein in the structure. So the pH matters. If I change the pH and I change the protonation, so say you have a minus charge, minus plus charge interaction here, because you have a O minus and an NH plus, and that interaction is helping to stabilize that. If you change the pH, you can change that protonation state and eliminate that attraction, and the protein will unfold. Call it denature. You can denature the protein. So there's a demo where we look at that. There's horseradish peroxidase rotating around. Oops, sorry. Oh, that is horrible. We're having some trouble with the screen resolution. I'm just going to turn the board off and on, bring it back to life here, see what the, stand by, We'll see if we can get you a little bit better pictures out there. Oops, broke it. Yeah, it'll take a second. You should start to see that. Is the resolution okay on that? How about that? Okay. Thanks for standing by there. We'll look at our horseradish peroxidase picture here. And we will do a little demo here where we take a peroxidase. Oh, Lord have mercy. Stand by. I am trying to get to a situation where we can see this a little better. So here we are. I've got some enzyme here. I've got some rutabaga here, actually, and that has a peroxidase in it. It's not horseradish peroxidase, but it's another root peroxidase. So we're talking about what's going on there, and I'm going to just zip forward until we can play with that peroxidase a little bit. Right in here somewhere. So I'm going to grind up the rutabaga, and there's so much peroxidase in the cytoplasm of the cells that just grinding it up, you can get peroxidase activity. You can get the enzyme to do its job. So I have some peroxide here, and I'll make two little yummy shakes of rutabaga, or a rutabaga daiquiri. If you have some ice and rum, rutabaga daiquiri if you want. Here is some hydrogen peroxide, and I'm going to put it in to that slurry. And like I said, so much peroxidase is present in that oh, this is the acid form. So I have this was acidified. You can see the pink. That was acidified. This is the neutral form. Why don't I do the fun one first? So this, the pH was so high that these started to be protonated, and the horseradish peroxidase broke apart. This, oh, I did it previously. This one was already done. Oh no, that was just the indicator to show you it was acidic. That was the peroxide. So now I put peroxide in both, and you can see this horseradish peroxidase, or this rutabaga peroxidase, is reacting and forming hydrogen gas and water from that peroxide, where this one, where we changed the pH so that those hydrogen bonding and charge bonding situations were disturbed, then this protein can no longer function. So the protein function is dependent on the pH, and now we understand why, because we understand that the pH tells us the charge states and what makes that protein stick together. Horseradish margarita, horseradish margarita, you would add tequila, I guess, and ice if you're out there. University of California doesn't recommend, does not endorse the horseradish drinks by any stretch of the imagination. Lord knows what I've done there. So let's continue then. Let's look at one of these polyprotic acids. So this is histidine, another one of your amino acids, and it has many protons on it that are potentially acidic. And in fact, it is a polyprotic acid with these 3 pKs. And you notice the pKa's increase. So let's assign them, and let's do a problem here. We'll sketch the titration curve for 100 mils of 0.1 molar histidine. As a 1 molar, very concentrated base is added. And then ask what species are present when we get to pH 8. So it's a weak acid. When we just add it into solution, it'll be slightly acidic, and I'm going to add the compound, or add the base to it. And you've seen some pKa's now. pKa around 2. That's one of the better weak acids we've seen. We've been using weak acids with pKa's around 4 and 5. So this is going to be quite acidic, and it's that proton responsible for that acidity, the strength of that acidity. So let's just do that. That proton there, highlighted in red, is that pKa, and this one over here, pKa 2, is that when it is in the plus state. And we know when it's in the plus state because we can compare pKa to the pH. So pH is below 6, protonated. pH is above 6, deprotonated. And pKa 9 is this guy here. So when that proton is on at pHs below 9, then that has a charge and this has a charge. There'll be times when this molecule has no charge because you'll have pHs where those charges balance out. So let's look at the titration curve. The first is an equilibrium between these 2 protons. They're the first 2 to come off. We're at low pH. So the pH curve can be sketched like this. It starts somewhere low, some initial pH. And we know it has 1, 2, 3 steps because it's a polyprotic, a triprotic acid. And we know 3 pHs for free. We know at each of these buffer region, the pH is equal to the pKa of the species, the predominant species on the molecule that is in equilibrium, half and half at those points. So the initial pH, less than 1.8, less than the pKa. We know it's less than the pKa because initially we put in mostly the acid form. And if there were equal amounts of the acid and the base form, the pH would be 1.8. So as I titrate, the first point that's easy to put on the titration curve is right there. Center of the buffer region, half equivalence. There's the first half equivalence point, and the pH is equal to the pKa of this acid equilibrium. And you can continue to do that. So now we'll talk about, well, what's the pH here? Now that pH would be calculated because now this is the only species there. I've titrated that proton completely off. That proton has been removed. At equivalence point, you know you've added a mole of base for every mole of acid, and this is the form that's present in solution, and that determines the pH. It is, of course, the equilibrium with this that determines the pH, but we know it is a pH somewhat less than 6 because we know this next acid has a pKa of 6. So the the curve is going to plateau there around 6. So equivalence point 1, we know it's less than 6. We're not putting a number on it. We're just drawing qualitatively what happens. We know it's less than 6 because that is the next plateau, and that was this proton being titrated. So this proton here, still attached at pH 1 and 2 and 3 and 4 and 5. But by the time you get to 6, half the molecules have those and half do not. So that equilibrium is this, half of them on, half of them off at pH 6. And both of those protons, all the molecules, have no proton there because we're way on the basic side of this pKa. So we have half and half now at pH 6, and you'd continue, you'd get to the equivalence point where you've taken all of those protons off. So here you're at equivalence point with all of those protons off, and again, you're going to make an estimate that that's less than 9.8 because you know the next equivalence point for that proton coming on and off is 9.85, and that has to be here. So you put that 9.85 is the pH now at that point, and the equilibrium is between protonated and deprotonated, half of this and half of this at that pH. So there you are, half equivalence of this titration, half of this and half of this. And then if you continue to add base, all those protons will come off and your pH will be determined simply because you're adding strong base to a solution that now is completely weak base and cannot do anything to affect the pH. You're removed all the protons and it's just the moles of OH that you're adding, no protons left to take off this molecule. Okay. That's the third equivalence point. It'll be something bigger than 9.9. And then very high pHs as you add simply straight OH minus to a solution that has no more acid to resist the change. Okay. So here's the amino acid cysteine at low pH. What is the total effective charge when I get to 7? So low pH, something less than 7. And by looking at that, you might be able to say that's less than 2 is that structure. I hope you can do that already almost, or at least are thinking about that. But that's the structure at pH less than 2. I want you to tell me what's the effective charge at pH 7. So let's think about that for a minute. We will take a vote. Is our resolution still okay? So this got teeny tiny itty bitty. I wish we could change the size of this. I'm just going to call the company and say, why can't I resize that? Okay, let's see what you're thinking. Push a button if you have not yet so far. This is bringing together a lot of stuff, and it comes so fast. And historically, I know you guys struggle with the pH equals pKa, proton off versus proton on. It's not a difficult concept. If someone explained it to you without all the other stuff we talked about, so if your mind wasn't clouded with all those definitions and everything that's happened, it is quite simple. And we'll look at the simple aspect and try to clear your mind here. So you are thinking, you have no idea. So we don't know how to make this any bigger. Timer count, anonymous, select screen. I'm going to talk to the company. This is just silly that's how big that is. So you are equally split between the three of them. And that may be because you don't understand, or it may be because you're distracted this morning. I hear your laboratory final for some of you who are in the lab is coming up in a little while. So what's going on here? pH 7. I've drawn it at this low pH, and I said to you, you should be able to tell it's at the low pH. Why is that? This proton is attached. And that proton is attached. That proton comes off around pH 2.2. It's half off by the time you get to 2. So if it's all on, I have to be below pH 2. So it is a low pH. This one, of course, we're way below that pKa. That proton's way on. It's not coming off for a long time. It's not coming off till we get up to pH 9. So it's fully protonated, and its charge is +1 because that proton is on at this pH. We want to get to pH 7, I think the question was. I should read the questions more, but let's just go to pH 7, see what the animation does, follow along. So here it is. That pH is much less than the pKa, so that's the acid form. pH is less. When the pH gets greater than the pKa, we'll get the basic form here. We haven't done that yet. At 7, then the pH will be greater than this pKa. So when we get to 7, in fact, we'll be 5 pH units above the pKa. You know, when we're at the pKa, equal mixture of acid base. 1 unit above, already 10 times more base than acid, and 5 pH units above is essentially all the base form. So predominantly the base form. There's always an equilibrium, as we know, but predominantly the base form. So that is going to go to the negative form. Do I do an animation? Yes, I do. This one, the pH is less than the pKa at 7, and it's quite a bit less. It's 2 units less. So this is fully protonated. So the total charge state is that minus and that plus the Zwitter-ion, they call that. 0 charge, 2 balancing charges in the molecule. So the overall charge is 0. Okay, if you understand that, you understand quite a bit about acid-base chemistry, pH versus pK, buffers, all that stuff. And we culminated here. We're kind of done with our acid-base discussion. We culminated here. We're going to do a few more examples. But this is the stuff that many of you will need to take home from this. What happens? How does buffering and acid bases affect what happens in biology? And this is the meat of that. Another interesting example, though, is your blood is buffered. So let's look at the blood buffer. Your blood is buffered by the fact that, we talked about this a little already, you breathe in oxygen and nitrogen, and that bonds to your hemoglobin, and it's taken to your cells, and then metabolized carbon dioxide carried by the hemoglobin back out through your mouth. So the carbon dioxide that builds up in your carbon dioxide gas from the metabolism of your sugars, that will acidify your blood. Carbon dioxide dissolves in your blood. It forms carbonic acid, as we discussed. So carbon dioxide dissolving, the gaseous carbon dioxide, acidifies your blood. But you don't want your blood to vary with how and when you eat or when you breathe even. So your body takes advantage of the carbonate buffer to keep the pH around 7 in your body. How does it do that? Well, the partial pressure of carbon dioxide in your lungs, if you're breathing consistently, keep batting the microphone, if you're breathing consistently, is about 40 torr, and that's quite low. 800 torr is about an atmosphere. So this is quite low. Not sure why I used torr there out of the blue, but quite low. So 20% of 5% of an atmosphere. 840 times 40 times 20. So a 20th of an atmosphere is about what you got there. So 20th of an atmosphere, though, we can calculate this equilibrium. We know about this equilibrium now. If you have that pressure, you can calculate the concentration of the carbon dioxide because you can use that KSP. I called it Henry's law here. We didn't really emphasize the name of that, but you get that from the Henry's law constant, the K, for the dissolving of the carbon dioxide gas in the liquid blood. And we're going to treat it kind of as water. Okay? So that's happening in your lungs. Your lungs is mediating that. And your lungs, you can breathe out that carbon dioxide and lower that partial pressure. So this will be kind of that equilibrium. The carbon dioxide is turned into carbonic acid very efficiently by carbonic anhydrase. That's one of those special enzymes in your body that mediates that conversion. It's quite good at it. So it makes the CO2 into carbonic anhydrase. It makes the CO2 into carbonic acid. And then the concentration of this carbonate here from the carbonic acid, those two, the carbonic anhydrase kind of maintains, by converting these two, this concentration at about 24 millimolar. So the weak base, that hydrogen carbonate there. So those things are happening in your body, in your lungs, in your bloodstream, in your cells, to keep those concentrations about where they are. So the CO2 concentration is about equal to the acid concentration because carbonic anhydrase is going to take care of that. And then these two have the natural equilibrium, acid-base equilibrium, and that concentration ends up to be about 24 millimolar when everything is working well. So what does that mean about your blood and your kidneys? Your kidneys come into it too, because kidneys get rid of stuff. So if this gets out of balance, so carbonic anhydrase is this concentration gets too high or too low, your kidneys can open up. Kidneys are one of the most amazing organs you have. They have these selectively permeable membranes, and they can kind of choose which compounds leave your bloodstream. They're a very incredible molecular sieve. And if this gets too high, you can pee some of it out. So a sophisticated method essentially of maintaining a weak acid and its conjugate base concentration so that your blood pH stays about the same. So when you do this, we know the pKa of carbonic acid, 6.1. So there's the titration curve. Here's the other proton coming off, the second proton coming off at pH 10. Hopefully your blood never gets there. Your blood stays around 7, and it uses this pKa to do that. So you can calculate about what your blood pH is based on these concentrations that your lungs, carbonic anhydrase, and kidneys are maintaining. So they maintain carbon dioxide slash carbonic acid concentration of about 1.2 millimolar and the conjugate base at about 24 millimolar. So you can use this expression. The pH is the pKa of the weak base over the weak acid, the logarithm of those two. And the pKa is 6.1. That's the one we're interested in. So the pH we can calculate. Just put those numbers in. The 1.2 from your lungs and carbonic anhydrase, and 0.24 from the carbonic anhydrase in the kidneys. And the pH of your blood hangs out at around 7.4. So your body actively working all the time, many systems of your body, to maintain a weak acid conjugate base pairing. There's a couple other acids in your body that help maintain that as well. So you may have noticed, if you may have seen this on the medical shows, if you watch the emergency medical response shows, sometimes they'll come across somebody who's hyperventilating, breathing very quickly like this. And what that does is it reduces the carbon dioxide partial pressure in their lungs. You're exchanging it with air too fast for any reaction to happen in your body. So if you're hyperventilating, that is bad. So this partial pressure decreases. So that decreases the acid form, and the pH of your blood will increase if you're hyperventilating. So it's a dangerous situation. You don't want to do it for too long, that rapid breathing. It often comes with some kind of stress response. And you have seen maybe on those medical shows, people say, okay, stop, breathe into this plastic, breathe into this bag. Have you seen that? Breathe into a paper bag, usually paper. There's not a, you wouldn't want to use plastic. Somebody doing this, the plastic would be, might cause another problem. You could see the EMT. Would you like paper or plastic with your hyperventilation treatment? Choose the paper. So you use the paper. And what does that help you do? That helps you rebreathe the carbon dioxide. It traps some of that carbon dioxide and helps keep the carbon dioxide pressure higher in your lung interface. So that prevents this from happening, cascading dramatically. And the pH of your blood going basic. Hyperalkylation is what that's called in the medical community. I read a study recently, though, that isn't really what happens. I think some people have done some studies. It turns out the sitting down and breathing into a plastic bag, or not plastic, breathing into a paper bag, probably doesn't affect the pressure of carbon dioxide enough to make that change and lower your blood pH. What they think is it's just a calming thing. People sit down, concentrate on the bag, breathing in and out, and it's the calming effect of the whole experience that seems to help with the hyperventilation. I don't know. Read the medical journal and see what the latest is on hyperventilation treatment. Okay, so some polyprotic acids can be indicators because when protons come on and off, that can change the structure and that can change the color. You take a proton off, you drop an electron back down into a set of molecular orbitals, and that's going to change the absorbance characteristics. It's even going to change the structure because bonds will get longer or shorter. And you'll change the energy levels within your molecule, and that has the potential to change the color. And if you have a compound that changes color with pH, we call that an indicator. And we've seen that in the titrations we've had a picture of. We've had the pink color is the acid, and the blue color is the base, and the yellow colors in the middle were neutral. So that's an indicator that is changing color because it's changing its protonation state based on the pH. So now we kind of know how they work. Here's Thymol blue, and I'm not gonna, I think I write the structure somewhere. I don't have the whole structure written out, but it's a diprotic acid. So when one proton comes off, it turns yellow. So with both protons on, it's red. One comes off, it's yellow. And that happens around pH 2, because that's that pKa. And then it turns from yellow to blue at around pH 8, because it loses another proton. pH is above 8, this form dominates. pH is between 2 and 8, it's yellow. And pH is below 2, it's red. So you have a very easy, straightforward understanding of how something could act as an indicator, because its color is a function of the pH, because it itself is a weak acid and has various protonation states, which just happen to change color. So there's pKa1 and pKa2. You could sketch the titration curve and the various colors of Thymol blue. So you can look at the color of the solution and say, about what pH am I at? And everything's in equilibrium. So if that equilibrium says you're pH 8 because of the color, then everybody else is obeying pH 8 equilibria in the solution too. Okay? I could ask, when it turns blue, what is the H3O plus concentration when half of it has turned blue? What is the pH? Well, the pH is 8.8, so the H3O plus concentration is 10 to the minus 8.8. So you know what those concentrations are because you understand how pKa's, pH's, and H3O plus concentrations are linked together. It looks like I might have a demo of that. How about we just push the demo button? And have it open. I've got this in this weird ass. Sorry. So here is a titration. So I have an indicator in there. It's acid, and I'm dripping in base from that burette into that beaker. So, oh poopy. I went all the way back to the beginning. You can watch me talk about this. What I should do is just go back and watch myself more. Okay, I think I got the slider. I want to go to just where I do the titration. That's somewhere in here. And go. So here's the solution. It's pinkish below the first pKa, so a low pH, something below 2. But you can see it's pinkish. It's a mixture of the red and the yellow already. I'm going to add base. And as I add base from that burette, I'm going to go up in the titration curve. So here comes the base. You can see it dribbling in. How's it look on camera? And you can see, look at it start to turn yellow. For full yellow, I'm in between now 2 and 8. And now I'm going to add a lot more base to get from 2 up past 8. So you can see I'm just letting it run in there because I got a lot of pH to go. But there it goes. It turns blue when I have a pH that is high enough to pull that proton off. I have to be above pH 8 to get it halfway off, and pH 9 or 10 to get it all the way off and make the blue form. Okay, so think of those titrations, the pHs, and pulling off the various protons. Hey, dude, what are you talking about that for? That doesn't have anything to do with what we're talking about. Oops, wait a minute, I have to shut the guy up. Where'd he go? I lost there it is, stand by. Sorry, guys. The audio on the YouTube is still running, so I'm trying to find it so I can stop it, and then we'll go back to the PowerPoint. Okay, here we go. Which of the pi to pi star transitions for the three forms of thymol blue? So there is thymol blue, not a very good structure. I should make a better one there. Apparently I just cut and pasted out of something. But there is thymol blue, has the various acidic protons on it. Which of the pi to pi star transitions, so it's some molecular orbital somewhere, and here are the three of them responsible for red, yellow, and blue. Which of them has the greatest absorbance at pH 10? Okay, so you know where the pH is, you know the color. Which absorbance am I talking about? A, B, or C? I won't tell you which is which, but one is red, one is yellow, one is blue. You tell me which one is most prevalent at pH 10. Okay, let's come back together here. Push a button if you have not yet. There's 5 or 10 of you that have pushed a button last time. Tell me what you're thinking. This quite a challenging one and really going back. So we're talking about pi to pi star transitions. We're talking about acid-base chemistry, structure, absorption and emission. Oh my goodness, it's everything. So let's see what you're thinking about everything. A and C are quite popular, and B is not as popular. So equally split between A and B. Let me tell you what my thinking is here. So these are the 3 transitions. So one is responsible for it being red, and one is responsible for it being yellow, and one is responsible for it being blue. So thymol blue at pH 10 we've established is blue because that last pKa 8, it turned to blue at pH 8ish and stayed blue at pH 10. So it's blue. So one of these transitions corresponds to making it blue. Now, blue are the highest energy photons. So you would say of these 3, blue photons would be absorbed here. That's the highest. If that's all your choices, red, yellow, blue, then you would say red photons absorbed here, yellow photons absorbed there, blue photons absorbed there. I think we can say that the highest energy are the blue photons. So we're already reviewing all of Chem 1 here. So, but a substance, if it's going to appear blue to our eyes, it cannot absorb the blue photons. So here come blue photons. Here's the thymol blue. Here come the blue photons. If they're absorbed, I don't see them. So it can't be absorbing blue if it's blue. We talked about that. It has to be absorbing the reds and the yellows so that the blues get through to hit me in the eyeball. So the likely answer is it's absorbing strongly in the red and appearing blue. Okay, so that's a beautiful description of so many things that you've talked about this semester. It appears blue, so it absorbs red. It's absorbing these. It would absorb, at pH 2, it looks red. At pH 8, it looks blue. So here it's absorbing the blues, and here it's absorbing the reds. Okay? Wonderful. Okay, so let's just, we're going to very briefly touch on, several people have asked this. If you look at a compound, what features of the compound make it acidic? What allows that proton to come off? And we're just going to spend, 10 minutes talking about this. There'll be at most one kind of easy question on the exam about this. And it's reasonable for me to put a question on the exam, even though we're doing it so late, is it relates to everything else you know so far. It relates to structure and electronegativity and oxidation state. So it's a fair thing to put on. And in fact, it makes it more interesting. Rather than just asking you about electronegativity or oxidation state, I can ask you, what's the acid strength? So let's do that. And by this time in the course, we should be bringing everything together. So predicting acid strength. I think intuitively you would think that the strength of the bond has to make a difference. The stronger that bond, the weaker the acid. If you can't pull it off, you can't pull it off. Okay, so that has to be everything else being equal. And every single one of these things we go through, it's going to be an everything else being equal situation. Then that would affect the acid strength. So everything else being equal, stronger bonds are weaker acids. But even without these numbers here, you guys should be able to rank these bonds because you can rank them by electronegativity. So this, I could have asked you a fair exam question. would be, now that I've told you this, arrange those by acid strength without those numbers there, because you don't need to know the exact numbers. You should be able to rank them by electronegativity and get the rankings of bond strength. Remember, the greater electronegativity difference, the more polar the bond, and the more polar the bond, the stronger the bond. And that, we're saying, is going to make it a weaker acid. So absolutely fair game on the final to ask you about bond strength, electronegativity, and acid strength all together in one question. So this is what has to happen. And the weakest acid is the strongest bond, and the strongest acid is the weakest bond. Based on our polarity and electronegativity, or the exact bond energies that we have here. Okay. And we can talk about the bond strength in terms of the free energy. This is kind of an enthalpic argument, and there's also the entropic argument. But delta G relates directly to the K. So we can get from this situation to the relative free energy differences of this reaction, because we can write the relative Ks, and if we can write relative K, we can write relative free energy difference. Okay, so these so-called quote-unquote oxyacids, the ones that are attached to an oxygen with a oxidizable varying oxidation state of the chemical of the atom next door. So chlorine next to oxygen, it's all a ClO bond, ClO bond, ClO bond. The question is, which is the strongest? And this, again, I think you have some intuitive idea. If you're going to talk about the strength of that bond, how far are the electrons withdrawn from that bond? So is going to be based on the oxidation state of this chlorine. So here the oxygen has an effect, but as this chlorine gets more oxidized, more oxygens around it, the oxidation number of the chlorine increases. That electron withdrawing effect weakens this bond, makes it a better acid. Weakens the bond isn't exactly the best way to say it, but we'll just hand wave and say that. It stabilizes this as an anion, and that stabilizing this as an anion makes the separation favorable. So, and that is reflected in the oxidation number of the chlorine. So you guys could calculate oxidation number of the chlorine, and if you have high oxidation numbers, you get stronger acids. So, and you can think about that as those positive charges or those oxygens reducing the strength of that interaction, making it easier for that proton to leave. Okay, and electronegativity. So here's a series of acids where the electronegativity difference is noted between an atom next door. So here it was an oxidation number of an atom next door. Here is the electronegativity, and same kind of argument. More electronegative, more electron withdrawing, stronger acid. So just very simple things that you don't have to study and read about in a book. Simply that explanation, I think, if you've been thinking about bond strengths and electronegativities and Lewis structures this whole time, which for some of you, you have, and all of you are supposed to, but geez, oh Pete's, there's a lot to think about. These are relatively straightforward qualitative questions that we can ask on the final. They're qualitative. You don't have to do a calculation, but you use stuff from the beginning of class for stuff that's in the end of class. And that's really what I like to do. I like to give you problems that think about one system, but think about all the things you can apply to that system. So predicting acid strength is a fun one to do there. And then this too, there's a remote ion effect. If you have hydrogens here, or if you have a chlorine here, again, these are all just electron withdrawing groups. If you do electron withdrawing groups, you get a weaker interaction here and a stronger acid. Or if you'd like to say a more stable anion, so you get a stronger acid. Okay? Which is the stronger base? Acetate, ethanoate, or carbonate? Acetate, we've talked about that. We know the numbers for that. This is ethanoate. This is carbonate. So we actually know, we look back in our notes, we've talked about the pKa's of those. So we know the pKb's. This is the the 2 protons removed there. And we were just looking at it. That was 8 or, no, it was all the way up at 10. I think those 2 protons came off at 10. This one, that proton comes off, that's acetate, so pKa around 4.7, so that one comes off around 5. What about that one? So just thinking about what you know so far about predicting the acid strength, do the reverse and, you know, pick the base strength. So whichever has the strongest acid has the weakest base. So pick the weakest acid among these to get the strongest base. Let's talk about that one just for a second. Take a vote, talk it in your small groups. Okay, guys, let's come back together and see what you're thinking. Push a button if you have not yet done so. You're going to fill out your course evaluations. So fill out your course evaluations. And I'm going to tell you something bluntly and frankly. Last time we did this, last summer, Zoom rooms were vital and people were talking. And every time I went in there, everyone was already talking. Now, I don't have to tell you this. I'm not even sure people are there. So I want to know why that is. Why do you feel like, maybe you have a feeling? Tell me in your course evaluations, if you don't mind, what is preventing you? And if you've done a group discussion in Zoom before, what's different and why is it no fun or hard to participate now? I have some ideas, but it was fully remote last summer. But everybody was in and chatting. They found people they liked. They got assigned in the things. And it was just like sitting with your friends, talking, making fun of me. I would enter the Zoom room and they would be making fun of me. So the camaraderie is not happening in this course. I'm sad for you. That removes the remote feeling. But I want to know why. So if you don't mind, in your course evaluation, and if you think you have an idea, tell me why that's the case. Or tell me when you see me someday. I'd love to meet all of you, obviously. So what do we have to do here? Let's see what you're thinking. It's kind of equally spread between the three. There's no majority for any of them. Stop. I started it twice. One person managed to vote. Okay. What's going on here? The stronger base. Which is the stronger base? I need to know the weakest acid here. So I need to say, if I were to put the proton back on, there, and there, and there, if I were to put the proton back on, which would be the weakest acid? Because why is it a weak acid? It's a weak acid because I hold on to that thing. Holding on to that thing means if I ever find one, I'm going to grab it, hold it, and not give it back. That makes me a strong base. That's what strong bases do. Grab protons, don't give them back. Acids, give them away. So if you're a giveaway person, you are not a very good base. You're a very good acid. So we have to look at that. And that's why I said we've talked about these. The pKa of that proton there is around 4.75. So we have a number for that one. And we looked at this one when we talked about the blood buffer. I forget what it was, but I think it's around 10. Did anybody look? Of that proton. So straight away, we can say this is the strongest acid between these two, the stronger between those two. So already, this is the strongest base between A and C. We could have got there without that, because we could have said, well, look, how's the electron withdrawing? What's weakening? What's weakening this bond? Well, that has one oxygen and a carbon. This guy has two oxygens connected to that carbon and withdrawing. Okay? So if I had to say that how strong is that bond, I would say, oh yeah, that is that guy says I am weakening that bond. What about ethanoate? I would say this one, there are no electron withdrawing groups. This bond stays pretty strong because there's no electron withdrawing groups there. It's just the carbons. So that staying relatively strong makes this a very good base. Once that's on there, it doesn't want to go. It's a weak acid. That being strong, don't want to lose it. So that means once I get it, I don't give it back. If ethanoate's in solution, it's going to rip protons off everything. It's an incredibly strong base. because this is a horrible acid. You know what the conjugate acid is? It's just ethanol. You put that proton back on there, you have ethanol. Do you associate ethanol, you know, what some of you kind of drink on the weekends here at Cal? Ethanol is just grain alcohol. It's a horrible acid. And yeah, if you take that proton off, it wants it back badly. This is an extremely, extremely strong base. I think the pKa of that guy is around 50. Okay, that is hard to get off. Okay. University of California does not sanction the consumption of alcohol among the undergraduate population. Let me just give you the disclaimer there. Interestingly, the pKa is around 50. I think the LD50 is around, I think it's around 50 grams per kilogram for ethanol too. Somebody Google that. LD50 ethanol. Leo is, this is a poison. And LD50 ranks how poisonous things are. 12. So it's 12 grams per kilogram. So LD50, what we're saying there, I'm saying, in case you can't hear me, LD50 is a poison ranking. LD50 for ethanol is 12, did you say grams per kilogram? Or 12 grams per kilogram. So with a density, you know, with a density of around 1-ish, 12 milliliters of pure alcohol is the LD50. What does LD50 mean? It means half the lethal dose. So 12 shots of alcohol is already half the lethal dose of alcohol. So be the alcohol police and don't let people do 20 shots a night. They're way past the LD50. Actually, and it's worse than that. It's not, you know, beyond that you die. It's the concentration at which half the population dies. That's how it's defined. So if you're at a party where everybody's doing 12 shots, half of you are going to die. So don't do that. LD50. Here's the PSA for the day. Don't be pounding the shots, 10 and 12 shots a night. Yes, you 1 in 2 chance of dying. Oh, here's just the explanation. So we talk about the conjugate acids. Oh, it was only, no, it wasn't 6, it was 10. This is 10-ish, yeah. So we look at the, that's the strongest acid. That's the next strongest acid. That's the worst acid, the weakest acid, strongest, weakest acid, strongest conjugate base. So we're bringing everything back together that we understand. We knew some pKa's. We looked at structure a bit to say, compare relative acid strength based on structure. So that wraps up our study of acids and bases. This is kind of neat. I will leave this one. Why don't we do this one in the review later? Because this is going to bring back everything from our thermodynamics and apply it to our bases. So I know it's already making your head hurt and it's late in the day. But here we're going to compare plots of standard state free energy versus temperature for various acids for which we kind of know their relative acid strengths. Okay, and we'll do that next time. Today we will sign out. In fact, I'll delay this one more. We'll do this on the review on Thursday. Tomorrow, we're going to talk about electrochemistry a little bit, and we're going to talk about electrochemistry very briefly You only have 2 days to study it up for the final. That's not fair. So I'm just going to introduce it, and I'm going to try to tell you exactly what you need to know, and do the darn homeworks. I should tell you that there's only one homework for electrochemistry. It is posted. Do it until you've seen all the questions, so you know what's going to be on the exam, because that's all that's going to be on the exam is questions that look like the homework, period. I'm not going to make up any new ones for electrochemistry. That's not fair. You just don't have any time. Okay? So there it is. Peace and love from Berkeley. Any questions? We have office hours Thursday. All right. Signing off from Berkeley.